Okay, so it's my pleasure to be here today, and I'm really looking forward to interacting with you. And I see that we have some real phase field experts in the audience, so you'll be able to keep me honest and pick up all my typos. So please let me know if you have any questions as we go. And so all of these notes will be posted. I'll make PDFs of them. This is the reason why I do this on an iPad, so that you have copies of them. But they are notes, and so that some of the things that I say will not be put on the iPad. So, but it'll give you a good idea of where we've been. So I'd like to start, for those of you who've never done phase field before, with the question of why phase field? Why are we here? And why is this even an issue? And so let me give you an example of a growth of a precipitate, a particle or precipitate, from a supersaturated solution. So you have a precipitate that sits here, and if you plot the composition as a function of position, it looks like this. So this would be your beta phase particle, this would be alpha. You have some sort of composition far away from the alpha phase that's given by the alloy composition, and you have compositions at the interfaces between the two phases, the equilibrium composition is given by a local equilibrium approximation. The equation, this precipitate grows by diffusion, and so you have to solve a diffusion equation where D is a diffusion coefficient, T is time. So you have a diffusion coefficient that you have, the diffusion equation that you have to solve in this outside, in the exterior domain. You know what the boundary conditions are for the diffusion equation. You know what the interfacial condition is at that position. And this particle is spherical of a certain radius. And this radius grows as a function of time. And there's a mass balance at the interface that gives you the growth rate of the particle. That's the gradient in the composition. And R is equal to R as a function of time. Okay, so that's the classic. If you go back to Zener, for example, this is what he wrote down for the growth of a particle. And so it looks like this is a fairly simple thing to do, right? It's a nice linear diffusion equation, right? It's just a nice linear diffusion equation with boundary conditions that you know, that are given to you. But the problem is the following. If you think about how you solve a diffusion equation, let's say you have a bar. You know the boundary condition at one side and the boundary condition at another side. You have this problem here, however, is that this boundary condition here has to be assigned at a position R, which is some function of time. Okay? So you say, okay, I'll give you the particle at some time, and then I can solve the diffusion equation. You have to know where to place this boundary condition, but you don't know where the particle is, right? Because it's growing. And it's growing according to this. And so if you could figure out where the particle is by this, you would know where to apply the boundary condition. But notice, this thing here, the gradient in composition, is set at some location as a function of time. And so you have this circular argument that you don't know where to apply this boundary condition because you don't know where the particle is, and you don't know where the particle is because you have to solve the diffusion equation, which you need for you need the boundary condition. Okay? And this strange coupling is a class of problems called free boundary problems. You look at this in the mathematical literature, they're called free boundary problems. And they're free boundaries because the shape and the location of the particle or the boundary has to be determined as part of the solution. And so before phase field models, what people would try to do is that they would take this domain and they would mesh it up and they would actually let the particle grow a little bit and try to determine the locations from this equation over here. And it would be very, very complicated, computationally really challenging, and nearly impossible when you get into shapes that are complicated, like you see in real systems like dendrites and other things. And so one solution to this that we're going to talk about in the course, and I'll put a question mark because you don't get something for nothing, okay? Solution is to write one or two, or many, well, let's just say one, partial differential equation that holds everywhere. And in other words, in both phases and at the interface. In other words, you don't have to track the, if you can do this, you don't have to track the location of the boundary. Of the interface. And it gets around this free boundary problem. And the basic idea here is to replace that picture that I showed you before over here, where you have this jump in concentration at the boundary, by something that's smooth, that looks maybe something like this. So you have some continuous function for the composition every place. You still have mass flow that flows down to drive the growth, but the overall equilibrium conditions at the boundary are built into this partial differential equation. And so basically what you're doing is that you're taking that sharp interface description that I gave you before, and you're giving it a certain characteristic width. And so that sharp interface is no longer sharp. You no longer have this jump in concentrations like you would do in the Zener model, but you have something that's diffuse over a certain distance, delta. Okay? And that allows you to write one partial differential equation that holds every place. And so these kind of phase field models go back to Langer, circa 1985 or so. And it's actually not published. There are a set of notes, famous notes, where he wrote down these phase field equations for the first time. And the reason why they're only notes is that he looked at that interface thickness and he said, well, gee, in a real material, that interface thickness is probably 3 nanometers, 10 nanometers. The domains we're interested in describing are microns. So you have about a factor of 10 to the third difference in the length scale between delta and the particle you're interested in. And if you have a factor of 10 to the third mismatch in length scales between delta and the particle you're interested in, you can imagine how many mesh points you need in a calculation to resolve this thing, as well, and these very, very long range diffusion fields. And at the bottom of the notes, he says, this is probably not computationally tractable. And then what happened is this thing called computers. And the enormous rate of growth of the power of a computer made some of these problems actually tractable and doable. And that's what we're going to talk about in the class. And so the key thing that you always have to keep in mind is that you don't get something for nothing, is you get the something, which is you write a partial differential equation everywhere. You can add new physics to the problem. It's very easy. The cost you pay is this thing, this delta. And the question always is how does that delta affect your results? If you're doing nanoscale materials, phase separation in nanoscale materials, delta isn't much of a problem because everything's on the scale of delta. If you're doing phase separation or growth of carbon, growth in steels, particle growth in steels, where you're interested in micron scale objects, this delta issue can become important. So that's something we want to make sure that everyone understands, and going forward. So that's why we use phase field methods, and they're based upon energies. Energies. They employ free energy functions. Free energies. This could be chemical free energies, and we'll talk. That's where we'll start. We'll talk about chemical free energies, but you can put in mechanical free energies, for example, elastic effects, electrical effects. If you wanted to have a model for the growth of oxides, for example, you can put in electrical energies, and etc. So it's an extraordinarily flexible method where you can add new physics relatively easily, because the only thing you need to do is come up with a new energy function that captures the energy function that's of interest to you. And so, in fact, during the course, we're going to be talking about chemical free energies. We're going to be talking about mechanical free energies. We're going to talk a little bit about elasticity, for example, and we'll show you how you can incorporate those in the context of a phase field model as well. But first, we're going to start with chemical free energies, just to try to set the ground and make sure everyone's on the same page, get the notation straight. For some of you, this would probably be a review, but for others, it will be helpful in kind of setting the context of these phase field models. We'll start with energies, chemical energies. And the simple model of this is the regular solution model. And it's really kind of it's called regular solution in the materials community. It's called Ising models in the physics literature. And basically here you have nearest neighbor bonds only. Neighbor bonds. The atoms are distributed randomly. On a lattice. And there's no vacancies in these models. No vacancies in the simplest kind of regular solution model. And so you have energies of the bonds. Energy of the bonds. And so you have an AA bond energy, which I'll call UAA, and BB bond energy. A BB bond energy, sorry, UBB. And an AB bond energy. UAB, okay. And so the idea here is that you have a lattice with A and B atoms. Okay, and you compute the energies by just basically summing the number of atoms that are near one another and next to one another and the bond energies themselves. These bond energies are negative by definition. And so basically by counting these bond energies and looking at the statistics of the you can write the molar Gibbs free energy as the mole fraction of component A plus the mole fraction of component B. So I'll define mole fractions in a second. The gas constant times temperature times and then plus what's really important for the regular solution model is this extra. Okay. All right, so Ca is a mole fraction, which is equal to the number of atoms of A divided by the total number of atoms in the system. And Cb is the same way. It's the fraction of B atoms over the total number of atoms of the system. So it's a fraction, and it goes between 0 and 1. G1, 0. These are the free energies. Free energies, which can be some function of temperature of the pure materials. Pure materials or pure elements, say elements. A. Pure elements. Z is the coordination number. Which is basically the number of bonds per atom. And the crucial thing is this omega, which is the regular solution parameter, which is related to the bond energies between AA and AB. Okay, so if you look at this this omega parameter here. So let's go back. So okay, so you have a couple of terms here that I want to highlight for you. So these are the standard state terms. In fact, probably not all that interesting. These are terms that basically just set the intercepts of the free energies with the axes CAB and CA and CB equal to 1. In fact, sometimes you'll see this written as this term pulled over here as a delta G, or the mixing energy. But these are the important terms in terms of what we're going to be talking about. So this one here is the classical entropy of mixing, right? See, this one here is the enthalpy of mixing. And so if you look at these two terms, as T goes to 0, this one disappears. So at 0 Kelvin, you only have the enthalpic contribution. And as T goes to infinity, no matter what I choose here, this term is going to dominate, right? And so at high temperatures, you get entropy of mixing. At low temperatures, you get enthalpy of mixing. And somewhere in between, you get a competition between the two. And that competition is what can lead to phase separation. So if omega is 0, and there's no, and I'll show you in a second what that means. If omega is 0, you have no preference between A and B atoms. You only have this term here, which is the entropy of mixing. And depending upon the sign of omega, you begin to change that entropy of mixing term. Okay, questions? Comments? Okay, most of you probably may have seen this before. So omega equals 0 is the simple case here where you have the no preference AB bonds. Omega less than 0, you want as many AB bonds as possible. And this is ordering, and we'll talk a little bit about that in a second. And if omega is greater than 0, you want as many AA or AB. And this gives rise to phase separation. And so what it does basically is it gives you a model of the chemical free energy that we need as an input to a phase field model. And so if you look at the molar free energy as a function of composition, let's say of A, mole fraction of component A, it looks something like this at a given temperature. These are the intercepts okay, so those are the standard state free energies. And this is for a case that omega is less than 0. Oops. Omega is less than 0. Equilibrium is given by a common tangent, or the constant chemical potentials, which is a common tangent construction that looks like this. And by construction, these are the equilibrium, what I've been calling C beta E and C alpha E. And this is the chemical potential of beta equals the chemical potential of alpha of component A. And this is mu A. B beta. Okay. So, all right. So let's go back. So basically to draw this, I've had to pick one particular value of omega. So let's go back and look at this picture here. So I have this free energy curve, and what I've done is I picked a particular value of omega. But it's pretty clear that these terms here are not functions of temperature, whereas this term certainly is, because you can see temperature sitting here. And so what that means is that this picture that I drew here, this one here, is clearly going to be a function of temperature. And at high temperatures, at high temperatures, this free energy begins to change. So it can go, oops. So what happens is that the height of the common tangent, this distance here, gets smaller and smaller until eventually you get to very high temperatures and that the wells disappear altogether. So if I plotted the free energy at very high temperatures, it would look like, basically just look like this. Very high temperatures. Okay? And so you can plot a phase diagram from this, and you just basically plot the locuses of those 2 points as a function of temperature, and it looks like this. You'll be seeing a lot of this during the course, and these are what I'm calling alpha and beta. And in the middle, you have a mixture of alpha plus beta. Okay, questions? Comments? I don't believe you. Okay, I'm going to give you a question. What phase is up here? Is it alpha or beta? First time I looked at this, I said, "This can't be right, right? What happens up here? Is it alpha or beta?" Okay, so no one asked this question, but I've thought about this before, and I think it helps in understanding what this phase diagram means. Is that this phase diagram is applicable for a material with the same crystal structure. Okay, and so the only difference between alpha and beta are the compositions of the phases, not their structure. And so you want to think of this as a liquid-liquid, FCC, rigid FCC, poured FCC, aluminum copper or something. So at very high temperatures, where the compositions of the phases become the same, you can't tell the difference. It's just one phase because it's always that same structure. And so this phase diagram is nice in the sense that it captures a lot of the fundamental physics of phase separation, but it's for a very specific system where you only have one particular, one structure. The other thing that will become important, as we'll see, are these points here, where the second derivative of the free energy with respect to composition equals to 0. Those are called the spinodal points. Yeah?
The structures are different. Then we can't get this continuous.
Right. Exactly. That's right. So that's precisely right. So if the free energies, if the structures are different, you don't have this this region in here where you have this inverted curvature of the free energy. That's exactly right. That's right. So if you had FCC, BCC, you couldn't draw a free energy diagram that looks like this. That's an interesting question. We'll talk about some deep issues associated with, for example, solidification, where you have liquid and solid, and you draw free energy curves that look just like this. So okay. All right. So so these spinodals are called these second derivatives of the free energies with respect to composition, are called spinodals. And they're very important because they give you the limits to metastability. Okay, and the free energy, the spinodals, and the actual phase compositions come to the same point at the critical point at the top here. So I don't want anyone to get confused. These dashed lines are not phase boundaries, but they're put on there to give a guide to the eye as the limits of metastability, and we'll talk a little bit about what that means. But they're basically put on there to tell you something about the free energy functions that are given here. Okay. One other thing I want to say before I move on to a different kind of free energy model is that You notice we're using a common tangent construction. To determine the equilibrium state. And let me draw this once more to try to make sure that everyone's on the same page, because this is kind of an important issue that sometimes is a little confusing to students the first time they see this. So let's say you have a free energy curve that looks like this. You say you draw the free energy, and what I claim to you is that these are the equilibrium compositions because they're where the chemical potentials are equal in the two phases. So mu A alpha and C alpha E is equal to mu A beta and C beta E and mu B alpha C beta E. Okay, those are the equilibrium. Those are the equilibrium conditions. Okay, so, and I drew this free energy kind of tilted for a good reason here, right? And so if you have a material that has a certain alloy composition, let's say here, that has an alloy composition there. That's a little bit too high for me to point. Let me do this. What this says is that if you started with a material at this composition, it will phase separate into two materials, two phases of different composition, right? Okay, so here's the question. Is this material here the lowest energy of the system? And the first time you look at this diagram, you say, well, of course not. It's here, right? That clearly has a lower energy than here, and it clearly has a lower energy than here. So therefore, everything must be sitting down here. And the answer is no. And it's not, because this composition is a conserved variable. Okay? And because it's conserved, you're not allowed to change this thing such that you can move it all the way over to here to get to that lower energy. Okay? So that's a very important idea. So composition is conserved. And this idea of conserved versus non-conserved will become important as we develop our phase field models. So let me contrast that with what's called the Bragg-Williams model. For ordering. And what you'll see is that this has much of the same sort of physics that the regular solution model is, but it's designed to describe ordering. Ordering in a compound. Ordering in a compound, and we're going to again take the very simple AB alloy and a BCC, body-centered cubic crystal, just to be really simple. And you have a crystal that looks like it's body-centered cubic. And you have A atoms, and you have a B atom that sits in the middle. And so every unit cell has, and it's identically ordered, looks like this. Okay, and so and this is, for example, a model for copper zinc. Copper zinc is kind of the prototypical L20 structure. And what these things give rise to what's called long range order. Because at t equals 0, everything looks exactly like this. all these and basically what the system is doing here is it's maximizing AB bonds. Okay? And you can see that you're doing this, right? So the AB bonds are on the other sides. So you think about this in 3 dimensions, right? In 3 dimensions, you have every one of these body center positions occupied by a B atom, and every corner is occupied by an A atom, okay? And what that means is that you can identify sublattices, and this would be the B sublattice, and this would be the A sublattice. And so you can identify these and you can call them A and B atom, A and B sublattices. And so the whole idea of the Bragg-Williams model is very similar to the regular solution model, is that at 0 degrees Kelvin, right, you have no entropy in the system, and everything sits on their sublattices. So in this particular case, all the A atoms sit on an A sublattice, all the B atoms sit on a B sublattice. As you heat it up, entropy begins to become important, and these things begin to interchange. And some of the B atoms end up on the A sublattice, some of the B atoms end up on the A sublattice, or vice versa. Okay? And at very, very high temperatures, everything is completely disordered and everything is random. So you don't have any ordering left in the system. And so you again have this interplay between entropy and enthalpy. Enthalpy meaning the bonds, entropy meaning it mixed up, the disorder in the system. The important thing about this model that I want to make sure everyone understands is that you'll notice what I'm doing here is that I'm changing the degree of order by just swapping atoms on a sublattice, right? I'm not changing alloy composition. I'm just swapping atoms on a sublattice. And so this model, I've put this in terms of a Bragg-Williams model, but it's precisely the same model for magnetic ordering, where you have spins up and spin down. So you can just change the degree of magnetic order by just flipping spins, right? There's no overall conservation law involved here. It's just flipping spins. And so you can go through exactly the same thing that I did before in the regular solution model by defining compositions. So for example, what we'll do is we'll define the composition of component B on the A sublattice. Yeah, number B atoms. On the A sublattice. And we're going to have CB is equal to the number of which is equal to a half in this case. And so you can define an order parameter which I'll call eta, 1 minus over CB, okay? And so this is equal to, so CB1 is equal to the number of B atoms on the A is equal to the number of A sites. Okay, so if you have no B atoms on the A sublattice, NB equals 0, and CB1 equals 0, and that implies that eta is equal to 1. System is completely ordered. Okay? If you have completely random alloy, which would be high temperature, the composition of the B atoms on the A sublattice is exactly equal to the composition of B atoms in the structure, which is a half. And so that means that since CB is equal to 1/2, that means that eta is equal to 0. So it's completely disordered. completely disordered. Okay? And so the order parameter tells you where you are. And I think you can kind of see already what's going on here, right? You only get a completely disordered structure where eta is equal to 0 at t goes to infinity, basically where the entropy completely dominates and the enthalpy is not important. You get a completely ordered structure at 0 degrees Kelvin when you have no entropy in the structure, right? Okay. So I kind of led you down the primrose path here to a certain extent, because if you look at this definition here, I've said, oh, I can identify a B lattice and I can identify an A sublattice, right? And I kind of drew it that way. But that's pretty arbitrary, right? I could have called this B lattice sublattice because you can have, so if you have all the B atoms on the B sublattice, it's completely ordered. But if all the B atoms sit on the A sublattice, that's completely ordered too, right? It's just kind of the definition of A and B sublattices. And so you can do the other limit where you have all the B atoms, the A sublattice, all the B atoms on the A sublattice. And that means that an A, which is C1b, is equal to 1. Oops, 1. And then so you have eta is equal to 1 minus 1 divided by a half, because that's the number of B atoms in the structure, which is going to be equal to minus 1. Minus 1. And so eta is completely ordered. And so in this ordering system, the values of the order parameter goes from minus 1 to 1, with 0 being the completely disordered system. Okay. So if you went through the statistical mechanics of this, you get exactly the same sort of free energies that we had before. They're a little bit different in terms of the, you write them in terms of order parameters, but you get a free energy that looks like minus n, which is the number of atoms in the system. You have the coordination number. I'll tell you what E0 is in a minute. But now instead of compositions, you have everything written in terms of order parameters. So I think it's pretty clear that this is the entropic term. In particular, you can see that this is a function of temperature. And then you have omega, which is the same omega I defined before. And E0 is basically related to the standard state free energies that I gave before, which in this case is just the sum of the free energies of the it's a constant, positive constant. And so if you plot the free energy functions as a function, if the free energy is a function of order parameter, they're bounded by 0 and 1. At high temperature, it looks like this. T greater than the critical point, it looks like that, where you have a disordered, completely disordered structure. Eta equals 0. You have something with, again, that looks like that. This is low temperature. Okay. Okay, so those look very similar to what I drew before. In fact, they're the same sort of plots, right? They look exactly the same. The big difference here is that this is an ordering system. And remember, in an ordering system, we're just changing atoms from one sublattice to another, right? And so this idea of eta is not conserved. It's different than composition. You can change eta just by flipping atoms, right? And so that means that the equilibrium is simply given by the partial of G with respect to eta equals 0. Okay? Unlike the common tangent construction where you had to worry about equality of chemical potentials, here it's just this. And so what does that mean physically? So let's do exactly the same thing I just did with the composition case. So I'll choose, let's say you started the system with a certain order parameter that sits here, right? A certain order parameter. And then you say, well, what's going to happen to the system? Well, the order parameter is not conserved, so this is just going to roll downhill. And in fact, that's the equilibrium part of the system, equilibrium, where the derivative is equal to 0. Okay? So it can actually just roll, or if you start over to here, it's going to roll down to here. Okay? Yeah. We'll talk about that when we talk about the Allen-Kahn equation. Yeah, and in fact, we'll derive the conditions for stability of that. I saw another hand. Oh, where does this 4 come from? That? Yeah. It's a combination of the definition of the order parameter and what we're talking about with the coordination number, and so it's definitely built into the whole definitions of the parameters and the order parameters and things. It's just algebra. Okay, so wait. So I didn't get a question that I thought I would get. Is that I just said that equilibrium is this. Okay, and that pretty clearly is here. But what about that? That satisfies that condition, right? And so that is an equilibrium condition. That is an equilibrium. If you took a system with eta equals 0 and you held it at that particular point, it in fact would be an equilibrium. But it's a special kind of equilibrium. It's unstable equilibrium, right? And so at this point here, unstable, and that's not a contradiction in terms. And the best example of that is if I was good enough here. So if I take my pen, that's equilibrium. That's stable equilibrium. Take the pen this way. That is equilibrium. If I could let it go, I don't want to. It's too expensive a pen. Okay, but it's unstable. So any small fluctuation will take it to this. And so that's exactly what happens at this point up here, right? It's unstable. So that's unstable equilibrium versus stable equilibrium. And it kind of gets back to the question that you just asked about what are the conditions for stability in these systems. So the key thing here that will become really important in what we're going forward is that some things are conserved, some parameters are conserved, and some things are not. And the conditions for equilibrium are different. For the non-conserved case, it's simply the derivative of the chemical derivative of the free energy with respect to order parameter equals 0. And in the case where composition is conserved, it's the equality of the chemical potentials that are at equilibrium that have to be the same. Okay? But the basic model looks precisely the same, and in fact it is. Okay. So, phase field models deal with dynamics used to describe a system, and the key thing here is evolution. So you have to take into account the fact that the system is evolving, and so this occurs by diffusion. Heat or mass in the system. So if you come from the solidification community, you would formulate your phase field models in terms of diffusion of heat. You come from more of the solid state phase transformations community, which most of you represent. We're more interested in the diffusion of mass, isothermal diffusion of mass. And you can kind of presage that that's what we're going to do because I'm talking about phase diagrams in terms of mass, okay, and not enthalpies in terms of heat. But you can do one or the other, and there's a very nice textbook that kind of treats this case with heat a little bit in more detail. It's by Prof and Elder. It's called Phase Field Methods. So Nick Prof came from the came at this from the solidification community, and so that's kind of built into the textbook that he wrote. It's a very nice and very comprehensive textbook that you can probably get online nowadays. Okay, so we're going to worry about in this course the diffusion of mass. So the A and B atoms, we're going to consider the case where we have A and B atoms in the crystal again. Crystal. And we're interested in evolution. And so evolution implies that the chemical potentials are not constants. So they vary in space. They vary in space. Vary in space. And so that means that there's going to be a force, F, on the atom, Fa, which is going to be equal to minus the gradient in the chemical potential of A, and the force on B is minus the gradient chemical potential on B. So F. Thermodynamic force. Why do you think I chose a minus sign there? Why the minus sign? And this is something that's going to become very important as we go. The minus sign is chosen such that atoms always flow down chemical potential gradients. They always flow down chemical potential gradients. You have fluxes of atoms. Remember, this is in evolving systems. You have fluxes of atoms in the system. And we're going to write this flux to inert markers, which I'll call M, or the lattice. Or the lattice. You can think of the inert markers as basically tracking the location of the lattice. That'll become important in a second. So you have a certain flux of atoms. So the flux is the number of atoms per unit area per unit time. You have a density of atoms, and you have the velocity of the atoms themselves, measured in this marker frame. So J is a flux, which is equal to the number of atoms per unit area per unit time. Rho is a density, which is equal to the number of atoms per volume. And so, and V is a velocity. And so you can see that the units work there because the number of atoms per volume times the velocity, which is the length per time, gives you atoms per unit area per unit time. This is a velocity. Okay, questions? So these fluxes are just basically the velocities of atoms. And you can have the same thing for the flux of component B. Measured with respect to the marker frame. So the velocity of each atom, A, is going to be moving. It's going to be moving due to the fluxes, due to the force. You can write them like this. Where M here are the mobilities of the atoms. of atoms, and they are always greater than 0. And so I'm asserting that this is the case. Actually, you can show that in order for the free energy to decay in an isothermal system, the free energy must decay and during any evolution process. And that basically means that these mobilities have to be positive. It just comes back to the fact that the free energy has to decay. Okay, so now we have these velocities. We have the relationship between the mobilities of the atoms and the forces. We know what the forces are. They're given by gradients in the chemical potentials. And so you can write the fluxes of A in this marker frame is going to be given by and the flux of component B in this marker frame. Okay, so I want to contrast that with Fick's first law, which says that J is equal to, you've probably all seen this, right? Probably J is equal to minus C. So you write Fick's first law. Is J the flux of A, or is it the flux of B when you write Fick's first law? D is a diffusion coefficient. How is it related to the mobilities? And so there's some interesting questions here. And in fact, if you look at these two equations here, you think about it a little bit. This is the chemical potential of A, and this is the chemical potential of B. Chemical potential of A is probably not equal to the chemical potential of B, right? Is the mobility of the atom A equal to the mobility of atom B? Maybe in some special cases it is, but in general not. And so you have two fluxes of A and B, but every time you wrote a diffusion equation in your undergraduate classes, you started with this thing. Say, oh, there's a problem here, right? Something's going on that allows me to take these two things and write them just like this, right? And that really kind of gets into the whole issue here of reference frames for diffusion and the frame in which these diffusion fluxes are written. And that turns out to be very important, because otherwise there's no way of you connecting what you've learned in your undergrad class with things like phase field models that just kind of sort of have this relationship but start off in this kind of representation of diffusion fluxes. And the key here is the reference frames for diffusion. And so imagine you're sitting here, you're in the class, so you're very happy. And you're watching these fluxes, right? You're watching these fluxes. And so you can have a flux with respect to the marker, but you can also have a flux of the markers themselves, right? And so you can have, let's say, the concentration, the density of A times the velocity of the marker frame. And you sitting on the banks of the river will measure a total flux, that's rho A times the velocity of A, which is related to the sum of the two fluxes. Okay? So imagine this is really a river, right? And you're standing on the banks of the river, and you have the marker particles, let's say little leaves sitting in the river, that give you the velocity of the fluid. And then within that fluid, you have diffusion, where the atoms are interchanging. And so the total flux that you get is different than the flux the flux of the individual components. And so the fluxes we were just determining were those with respect to the lattice, but then you can have the velocity of the lattice itself. Okay? And so what we're going to be doing, and I won't go through all the details of the mathematics, we don't have time for that. But basically what we're going to be doing is we're going to be taking the marker frame here to be equal to the center of volume volume frame. Center volume frame of reference. And what that means is that it's a marker frame such that the total volume of the system is equal to 0. And implicit in this, so the way to really kind of put this is that the partial molar volume of A and B are equal. And if you think about this in terms of a crystal rather than a fluid, it says that the vacancy concentration is always at equilibrium. And so basically I'm just going to give you the essential equilibrium. Okay? So, and I do this, it's more important than seeing the algebra of how you go here, but these are the assumptions. Vacancy concentration always in equilibrium, and the partial molar volumes of a component A or component B are the same. So that as the fluids intermix, the volumes don't change. Okay? And the vacancies are always there in order to provide lattice sites to keep the things moving around. Okay? And those two assumptions will become critical. I think there was someone who's doing spinodal decomposition in confined volumes, right? That's a real problem. This can be a real issue in those kind of situations. Okay? So if you do that, if you write these fluxes in this volume frame for diffusion, the nice thing about that is that you've replaced these two fluxes in this volume-centered frame now. They're equal and opposite. So V is equal to the volume-centered frame. Volume-centered frame of reference. Okay. So you write these in the volume-centered frame of reference, and you get an equation for the diffusion coefficient that looks like this. It isn't at all obvious how you get there. In fact, it's about 7 pages of algebra. Okay, but it's relatively straightforward. There's a nice review article by John Hilliard that he wrote on the spinodal decomposition back in the 60s or 70s, where he very clearly goes and carefully goes through that. So if you want to see the references. So Vm is a molar volume of the crystal. And this is sometimes darkened. So you can see sometimes people call this darkened diffusion. From the standpoint of phase field models, one of the important things that we have to keep in mind is that all of these terms here are always greater than 0, right? The mobilities and the concentrations, they're greater than 0 by definition. So let me talk a little bit about this term here. The derivative of the molar free energy with respect to composition, Cb, is equal to mu B minus mu A. Okay? And so J, the flux of B, is proportional to gradients mu B minus mu A. For those of you who don't remember, I don't want to quick review of thermodynamics, right? So mu A is equal to the derivative of the free energy with respect to the number of moles of A. The reason why the derivative of the molar free energy with respect to the mole fraction is equal to the difference is that you're normalizing things by the number of moles in the system, right? They're mole fractions and gives free energy per mole. Okay, so the flux in B is related to the gradients in the difference in chemical potentials, and this is sometimes called a diffusion potential. And when you think about it, so we're in this reference frame where JA is always equal to minus JB, that the flux that you see in the system is related to the difference in chemical potentials. It kind of all seem to all kind of sit together, right? Seem to all sit together. Okay, so let's. Oh yeah, sorry.
We have a good vacancy concentration is at equilibrium is clear. But why the molar volume or restrictivity?
Yeah. So if you're in the center of volume frame, one of the assumptions that this equation makes, this one here, to get to here, you say that you're in the center of volume frame and that as A and B interchange, the volume of the bar doesn't change. In other words, you don't get fluxes due to the fact that the volume is changing. If you get fluxes due to the fact that the volume is changing, you'll get a different equation here. And so what people typically do, and I know what you're getting at, actually, because what we'll be doing later on is we'll be doing phase field models where you have stresses, and VB is not equal to VA, and you generate the stresses. Okay, and so those are typically elastic stresses, which are small differences in the partial molar volumes. So this extra flow that you would get due to this center of volume frame is small. So you don't have to worry about it. But if you were doing a solid vapor phase transformations where you have big differences in molar volumes, big differences in volumes, you can have substantial flows due to the diffusion process, for example. It might be important. Okay, so let me talk about this term that's the partial of G with respect to the composition. So what I'm going to do is I'm going to take this gradient operator here and pull it through that equation. And so JA becomes equal to minus, I know I'm going to write this in terms of rho A. It doesn't matter, JA minus rho A, rho B, molar volume. Times the second derivative. Okay, so the first derivative becomes the second derivative, and you have this. Yeah, let's rewrite this in terms of mole fractions. So you can get and so if you wrote a typical diffusion equation that looks like your fixed first law, you conclude that the diffusion coefficient is basically all of this stuff here. Okay, so this is the classic interdiffusion coefficient. Interdiffusion coefficient, okay? And so the thing that's really important is, from the standpoint of what we're talking about, is this, is that is in the problem. And so the thermodynamics dictates that the fluxes are related to which is the reason why I emphasized zero. And so you have these regions in here where this second derivative it's less than 0. And out here, it's greater than 0. It's greater than 0. And so let's go back here. So what are the implications of this? Well, look at the definition of the diffusion coefficient here. It has this second derivative. And if you think about this equation here, if D is positive, the fluxes are down composition gradients. If D is negative, the fluxes are up composition gradients, right? So D tilde can be negative. Negative, that means you can have fluxes up concentration gradients. Up concentration gradients. And that is an interesting problem. Think about what's happening here. So, okay, I want to make sure that everyone understands. You have fluxes up composition gradients, but are the fluxes going up or down chemical potential gradients? Okay? And that's basically a failure of classic, simple Fickian diffusion. And we'll talk about the implications of that after the break. So thank you for the questions. That's the total density of the system. 1 over the molar volume. Other questions? Yes? Yeah, so, okay, go all the way back to the, yeah, so we go all the way back to why are we here? So delta here is on the order of nanometers, right? In most systems, except in polymers, for example, they can be very big. But let's say in crystals, they're on nanometers. And then you have these long-range diffusion fields. Okay, these long-range diffusion fields scale with the size of this, the size of the particle, not with the size of delta. And so if you have a long-range particle that's on the order of a micron, this is on the order of tens of microns. This is on the order of 10 nanometers. You have to put, as you'll see, in order to solve for this composition profile, you have to put mesh points, 8 mesh points, 6 mesh points here. And so that means you need 6,000 mesh points just to cover one precipitate versus all the precipitates you want to model in a real system. And so the question is, what do you do? How do you handle that? And the first thing you say, well, just make delta bigger. Make it microns. Then you're okay. But then you're not using the real delta of a true system. And you can ask questions about how does that affect the answers? And it turns out it does, and it can. And so that's where the care you have to use in the phase field model is understanding what the effects of this is when you don't use something that's really on the true length scale of the problem. And so, for example, we will write down a model for grain growth that allows you to use deltas on the order of microns, even though the real grain boundary width is on the order of nanometers. And we will very precisely determine how bad that approximation is and when it works and when it doesn't. That's really one of the key issues with phase field models. Did that answer your question? But if you're doing a nanoscale precipitation problem, like if you're doing phase separation in a nanoparticle, that's 20 nanometers, then you just use the regular true width and you're okay. Okay? You don't seem convinced. Oh yeah, so you can use, right, that's right. So you can use grids that are basically conformed to the interface and coarsened out. And we can talk about how or why those work. They work very, very well when the total interfacial area per unit volume is small, like one dendrite in a huge domain. But if you have many precipitates with many interfaces, you need a very small grid to capture it. So then if the surface area per unit volume is high enough, you don't win by doing that. But sometimes you do. And if you have a clever computer code that unmeshes and meshes very quickly, you can sometimes win.